Continue on with lecture from Monday, right? If you missed Monday's lecture, it might be a little bit confusing for you, so make sure you watch the videos. Um, Only two things we're talking about for the last couple of weeks, electrochemistry and thermodynamics, which is not very big chapters, so that's a good thing, right? But you still have to be able to relate the two, make sure that you know what's going on. So, um, if you recall, on Monday, right, what we were talking about before was the standard cell potentials, right? And with the standard cell potentials, right, in standard conditions, everybody remember what the standard conditions are, right? 1 molar, what was the temperature? We had a big discussion about the temperature. Yes, 298, right? Remember to convert anything from Celsius to Kelvin, you just add in the 273, right? And so that's what that was. That's the standard temperature. 1 molar is the standard concentration. 1 atm is the standard pressure, right? All that stuff. So all that stuff is all standard. So when you get those things in an equation, then you know to use those, right? In those letters, those are variables that you don't know what they are yet, right? So what you can do then is you can get the reduction potential of the cathode and the reduction potential of the anode, and then that will actually give you the cell potential, right? And the cell potential is it's very similar to like if you have a battery and it's like a 9-volt battery, right? That's the cell potential of a 9-volt battery, for example. Or if you have a car battery, right? The car battery is 12 volts, right? 12 volts, right? So that's the cell potential right there. But you can also use that because it is the same thing as that cell voltage potential that's in batteries is the same thing that we do in all chemical reactions because what electrochemical reactions because what is a battery but a chemical reaction, right? You hear things like lithium ion batteries. So what do you think is the ion in lithium ion batteries? Lithium, right? Or car batteries are usually sulfuric acid, right? Um, Alkaline batteries, everybody knows those. So, and then the other thing is you can get the cell potential by getting the standard reduction potentials of the cathode and the anode, and oftentimes you can find that in the chart that I was telling you about before, right? Um, and if you weren't here on Monday, just to be clear, somehow when I made my PowerPoint, all the arrows here got turned into A&E logos, American Eagle logos, right? So all those A&Es right there should be arrows, okay? So knowing what a cell potential is, right? Knowing what a cell potential is, right? Just know that there's a difference between having the cell potential, right? Which is the difference between the two standard reduction potentials, right? The standard reduction potentials are the reduction potentials, like the tendency for one of the electrodes to lose an electron, right? Whereas the cell potential is actually the difference between the reduction potential of the cathode and the anode. Okay, so expect questions in the multiple choice section about the relationship between these things here. Okay, so we already answered that question. So let's take it to cell potentials now, right? So if you have an anode of the cell, right, and the anode's reduction potential is negative 0.76 volts, right, and the cathode is its reduction potential is 0.37 volts, right? Again, these numbers come from a chart. They've already been determined for you, and they come from a chart, right? And then you can figure out what the entire cell potential is, right? Think of it as a battery, right? By plugging it into that equation I just showed you a second ago, which is right here, the difference between the anode and the cathode reduction potentials, right? And so all you have to do is 0.34 volts, and then minus, and then you do the you do minus, and then you do the negative 0.76 from the cathode, and that gives you a total of 1.1 volts, right? 1.1 volts. That's kind of like a double A battery. Well, I think a double A battery has 1.5 volts, right? So this is just a picture here describing what a cell potential is, right? So we have a zinc copper solution with zinc and copper in there as the electrodes, right? The zinc is the anode, right? Yeah. Oh, that's weird. I know. I just saw that. Ah, killing me. Okay, um that's really weird. I wonder why. This right here is wrong, right? The numbers are correct. This is a typo. The anode should be over here, and the cathode should be over here. The numbers are correct. It was just a typo. Okay. Yeah. It should be cathode minus anode, right? Okay. Yeah. So I don't know why that happened. That's really weird. That's super weird. I don't know why that happened. Anyway, too fast typing, I guess. Anyway, so back to what I was saying before. I apologize for that. Make sure in your notes you fix that, right? Because I don't want you to. Well, on your exam, I'll give you the equation on the exam. So I guess you don't have to worry about that, right? So, but on the exam, I'll give you the equation. But just for your references, and when I guess while you're doing practice problems, right? Make sure you're subtracting the anode from the cathode, not the cathode from the anode. That's really weird. Okay. All right. So here's an example of what the cell potential is about, right? An image showing you what the cell potential is about, right? We have here a salt bridge connecting a zinc solution with a copper solution. The anode is the zinc, right? And then the electrons flow away from the zinc, right? So that's why it's the anode. And then they go towards the cathode. The electrons are flowing towards the cathode right here, and the cathode here is copper, right? And so we were talking about this before, right? On Monday, where the zinc metal, right, actually loses electrons. It becomes zinc 2, right, as the electrons leave, giving you, if you have a voltmeter there, you can actually test and see what the voltage is of the cell is here, and it gives you 1.1 volts, which is super close uh, to the actual experimental, right? Like if you did the experiment and you read the number, it's actually very close, right? And then they go towards the cathode. The copper here, right, is actually receiving those electrons. So interestingly enough, at the very microscopic level, and I talked about this a little bit on Monday, right? If you leave the zinc here for too long, eventually you'll run out of, it might take a gazillion years, right? But eventually you'll run out of zinc because all the zinc becomes zinc 2, right? But the cool thing about it though is that as those electrons flow over the circuit right here over to the copper electrode, the copper twos in this copper sulfate solution actually become copper. So as the zinc goes down, right, like it's less, you lose the zinc metal because it becomes zinc ions. You actually turn the copper ions into what? Copper metal. So you get more copper. Right? Isn't that cool? So eventually, if you left it there for a couple, maybe a few years, I don't know why you would do that, but if you left it for a couple years, uh, you'd run out of zinc, right? Because it all go into solution, and you have a really big piece of copper, right? The copper would increase, right? So that kind of relationship is something that you need to know, okay, for the exam, okay? Because I will ask you questions like, if I have this and this solution and this and that solution, this is the anode and this is the cathode, right? What will happen to one of them over time, and what will happen to the other over time? Does that make sense? Okay, so I really need you to, those are the kind of questions I might ask you on the multiple choice part of the test, right? So again, here's the standard reduction potential right here for the zinc, right, at negative 0.76. Standard reduction potential here for the copper here at 0.34, right? You plug it into the equation and you get 1.1 volts, right? And just so we're clear where that number comes from, where do we get the negative 0.76 and where do we get the 0.34, right? Which you saw this chart already before in the lecture, right? But let's go back anyway to make sure that everybody's clear on this. We'll go to the chart that's missing arrows and has A and E logos on it, right? We have here zinc, right? Negative 0.76. Copper here, right? 0.34, right? So 0.76, remember that was actually in a negative parenthesis, so that turns into positive. So 0.76 plus 0.34 is what? 1.1 volts, right? Make sense? That's where those numbers come from, okay? So make sure that you know that we're not just making up these numbers. They come from somewhere, right? And you can use these numbers in the calculations that are going to come up. Okay? All right. So, okay. So, oxidizing and reducing reagents, we talked about this before, uh, right? When you have an oxidizing agent or reducing agent, it's just the opposite of what's getting oxidized and reduced, right? But what does it have to do with the reduction potentials, right? Well, the more positive the value of the reduction potential, the greater the tendency for reduction to occur under standard conditions, right? The greater the possibility, right? The tendency for it to occur under standard conditions. So the strongest oxidizers have the most positive reduction potentials, right? Which makes sense because it's such strong oxidizers. What do they like to do? Rip off electrons, right? They like to take electrons. And then the strongest reducers have the most negative reduction potentials, right? The strongest reducers have the most negative reduction potential, right? So here is a nice little chart that's in your notes of the increasing strength of oxidizing agents, right? We start down here with lithium. We go all the way up here to fluorine, right? And then over here, we have fluorine, the ion, going all the way down to lithium metal, right? So again, the more positive the reduction, right? The more positive the sorry, let me say that again. The more positive the value of the reduction potential, the stronger the oxidizing agent, right? The more negative the reduction potential, the more negative the reduction potential, right? The more difficult it is to reduce, right? The more difficult it is to reduce, right? And vice versa, okay? So that's just a chart that kind of demonstrates these key points right here, right? These two things. These are very important points. Strong oxidizers have most positive reduction potential. Strong reducers have the most negative reduction potential. Okay? So that brings us to our very first question for today, which is the following is not true about oxidizing reducing agents, right? A, the more positive the value of the reduction potential, the less tendency for reduction under standard conditions. The strongest oxidizers have the most negative. The strongest reducers have the most positive, or none of these are true. The first time I think I put a choice up there that says none of these are true. Okay, so just to go over, the strongest oxidizers have the most negative reduction potentials. Actually, no, that's the opposite. And then the strongest reducers have the most positive reduction potentials. That's actually opposite. And then this one here should be the more tendency for reducing, right? The more the tendency. So the answer there is D. All right, so here's another equation that you need to worry about here, right? Sorry, not worry about, but no. Okay, spontaneous spontaneous redox reactions produce a positive cell, right? Or EMF, not the electromagnetic frequency that we do to detect ghosts, but the electromotive force. And note that for all redox reactions, this is true, not just voltaic cells, but all redox reactions, this is true, right? And so since there's a Gibbs free energy measure of spontaneity, you can actually use, there's an equation that actually relates Gibbs free energy, right, delta G, into the reduction potentials, okay? So here is how they relate. Delta G actually equals negative N F E, right? So delta G is the same delta G that we've talked about before, right? The state function from the thermodynamics chapter, right? N here is the number of electrons, okay? And then F here is called Faraday's constant, which Faraday's constant is right there, 96,485. And then E is the reduction potential, right? So just know that a positive EMF, right, or a positive cell potential means what? A negative delta G. Why? Well, if you put a positive cell potential here, right, which means that the E is a positive number, and the negative number in front of the negative sign in front of N multiplied by the positive number of E makes what? A negative number, right? And that's why when you have a positive uh, cell potential, you get a negative delta G, right? What's true then of the opposite? If you have a negative cell potential, then what is delta G? It's positive then, right? So again, that is one of those relationships that you need to know for the last exam, right? and for the final as well. But right now, let's worry about the last exam. Know this equation, right? And I'll probably give it to you on the test, right? But when I ask you a question, like if I have a negative reduction potential, what's my G going to be, right? Negative or positive? Okay, make sense? Most of the it is good stuff. Most of the equations you'll be using, right, won't even be calculations. It will be me asking you about the charges they will be, right? Whether they're going to be spontaneous or non-spontaneous and things like that. So you can actually then relate, right? You can actually then relate the free energy, that gives free energy, right? The oxidation reduction, right? The reduction potentials, right? No, cell potentials, and K. Because remember what K is? K is the equilibrium constant, right? K is the equilibrium constant, right? So here we have delta G, right? Standard delta G, right, or G naught, standard delta G is equal to this again, the negative NFE, which we saw in the last slide, but then that also equals what? Negative RT ln K, which we talked about back in the thermodynamics chapter. Remember that? Right? We talked about that in the thermodynamics chapter. Okay? So you can actually go back and forth between delta G, the standard reduction potentials, or reduction potentials in general, and K, right? So let's start right here, right? If I have a standard reduction potential, right? If I have a standard reduction potential, I can plug that in there, okay? And then I can plug in the ideal gas constant, the standard temperature, Faraday's constant, the number of electrons that are being moved, right? And then what can I solve for? K, right? Exactly. But then I can do the other way too. If I have a K, right, I can plug in K there. I can plug in Faraday's constant there, the number of electrons being moved, the standard temperature, the ideal gas constant. Now what can I get? The cell potential. Make sense? Right? Or the standard reduction potential. Make sense? Right? You can even go this way. You can go reduction potential to standard delta G, which we already did that before, right? If I have an E, if I have the standard reduction potential, right, I can plug it in there. And of course, those are all in the freaking chart that I showed you a few seconds ago, right? And then you put in Faraday's constant, the number of electrons being transferred, right? Solve for that equation, and what do you get? You have a delta G now, right? And then vice versa. If you have a delta G, plug in delta G there, plug in the number of electrons being transferred, Faraday's constant, and what can you get? The standard reduction potential. Make sense? Right? Like all three of these are related to each other, and that's the reason why I wanted to put the thermodynamics chapter with the electrochemistry chapter, right? And keep it away from the acid-base chapter because they are related, but not as well as this. Because now you can also even do this, which we saw in the thermodynamics chapter. Delta G, if I have that, I can plug that in there, ideal gas constant, temperature, and then I can solve for K, right? If I have K, plug in K there, right? Ideal gas constant, standard temperature, what can I get? Standard delta G, or Gibbs free energy, right? Do you see the relationship there? Know this relationship, okay? Know this relationship, okay? So, let's talk about non-standard conditions then. For non-standard conditions, we have this thing called the Nernst equation, right? And in the Nernst equation, right, let's see how we get there first. How do we get to the Nernst equation? Well, remember this right here, delta G plus delta G standard, uh, uh, delta G equals standard delta G plus RT ln Q, right? That was an equation that I gave you back in the thermodynamics section. Remember, does anybody remember what Q is? It's a reaction quotient, right? So remember Q and K, they're equal to each other when? Q and K equal to each other when? Yes, they're equal to each other when you're at equilibrium. So what is the difference between Q and K? K is the equilibrium constant, right? Whereas Q is the conditions at any point in the reaction at all, right? So you can figure out what the reaction quotient is at any point in the reaction, okay? But once you get to equilibrium, then Q equals what? K, Does that make sense? Okay, so if you take this delta G right here out and substitute it for negative NFE, which we saw on the last slide, right? And then this one here too, and substitute for NFE, right? Then we get negative NFE equals NFV standard plus RT ln Q, okay? What we can do now is then divide both sides by negative NF, right? Which is divide both sides with the number of electrons in Faraday's constant to the negative. And what we end up with is this. This is called the Nernst equation right here. This is called the Nernst equation, right? At non-standard conditions, right, the cell potential is equal to the standard reduction potential minus RT divided by NF ln Q, okay? So the electrochemists out there, though, they don't like using ln a lot, right? They don't like using ln a lot, so they actually converted it to log, right? They converted it to log by putting in the 2.3, 2.03 there, right? And when you put in when you multiply 2.03 to the e, well, let me say that one more time. You can convert an ln to a log by including the 2.303, right? And the reason why I wanted to say that again is because I wanted to ask you, right? Because the very first question people ask me is, where does the 2.303 come from? Does anybody know? Anybody know? Where does the 2.303 come from? Why can we use this and put it right here, right, and get log instead of ln? Some of you are in college algebra right now, aren't you? Oh, that's even better. Pre-cal is even better. Pre-cal is actually the class you take after algebra, by the way. That's what I'm saying. Calculus is after algebra. Remember that this is called a natural log. How do you undo a natural log? Oh, say again? No, no, not the natural log. Yes, Kiara's got it right. It's E, right? To the E, right? So E to the something. And remember that E is equal to what? 2.17. Wait, 2.71? Somebody put E into their calculator. It's either 2.17 or 2.71. I can't remember. Just type in E. There should be an E button on your calculator. Huh? What? It's an error? You should be able to just type in E and get a number. There it goes. So that's what it is. E is 2.718, right? And the reason why you can actually just go from ln to log is because log means log base 10, right? Does that make sense so far? Log means log base 10, right? So you want to somehow get this ln to become a base 10. And how do you make it become a base 10? It turns out all you have to do is do E, right, which is 2.781. Is that what it was? Oh, 2.718, right, to 2.303, and that gives you 10. Do it. After you do that, you can plug in the standard temperature and the ideal gas, right? And then the Faraday's constant, and then what you end up with now is is this number here, right? Which will always be the same, 0.0592, right? And now you can solve for either the cell potential at non-standard conditions, right? Or any of the ones that you haven't solved for yet, okay? So I want to do a quick example for you here, okay? I want to do a quick example, okay? Oh, I forgot to change it to, this is the only kind of math that you'll have to do in this chapter, okay? So remember that we had the equation, right? We had the we're talking about zinc, right, becoming, sorry, I didn't mean to do that arrow. I meant to put plus. Zinc plus copper 2, right, becomes zinc 2, right, and copper. Okay? Remember that? That was the equation that we had. That was the reaction that we had a couple minutes ago on the PowerPoint. Okay? So remember from that PowerPoint of that slide a couple of minutes ago that the standard reduction potential here, right, was what? 110 volts, right? That was that 76 plus what? 34, right? From the chart. Okay? And then how many electrons are being moved from here to here? Huh? How many electrons? 2 electrons are being moved from here to here, right? So what does N equal? N equals 2, right? And then everything else is what? A constant, right? Everything else is a constant. Okay, so quite literally, all you have to do then is say, E, just like in the Nernst equation, equals 1.1. I keep on saying 110. I apologize. It's 1.1 volts, not 110 volts. But 1.1 volts, right? Minus, right? And then this number down here, right? That number right there, because we've already plugged in all the constants. The constant is the standard, sorry, the constant are Faraday's constant, the temperature, and the ideal gas law, right? And so that's why we get this number right here, right? And so we put that in there. So that's minus 0.0592, right? And then what goes under the 0.0592? What does it say in the equation? N, right? So the number of electrons that you got, right? The number of electrons, right? So now what do we do with the Q here? What is Q like? Equals what? Q equals what? Q equals K at equilibrium. And so when we do an equilibrium expression, what do we always do? Products over reactants. Remember that? Right? So what is the product over reactants here? The product here is zinc 2, right? And what was the product? Copper 2, right? Don't forget everything you learned before this lecture. So log, right? And then that's going to be then the concentration of zinc 2 over the concentration of what? Copper 2. See? All that stuff there will give you the cell potential, right? So say I gave you concentrations of both zinc and copper, right? And say I said the concentration of copper 2 was, say, 5 molar. And say the concentration of zinc 2 was 0, zinc 2, that's not zinc, there is zinc 2 equaled 0.05 molar. What would I do? I would plug in the copper down here, right? I would plug in the 0.05 up here, right? And then just solve. Yes, because look, right here, log, right? Remember we went through that whole rigmarole trying to figure out how we got from natural log to log, right? With the 2.303, right? So then you just plug those in, right? Yes, that is correct. And so your equation then becomes this. It's going to be E equals 1.1 volts, right? Minus 0.0592 divided by 2, right? Log of what? Exactly. 0.05 over 5, right? And then you just solve, and then you get the then you get the reduction potential at non-standard conditions, right? And then so E then equals should be 1.16 volts, right? So the really cool thing about this is that if you're ever stuck out in the desert, right, and you need to start a car because your battery's dead, right? If you have a copper electrode and you have a copper electrode and you have a zinc electrode and you just happen to have like some zinc chloride with you and some copper chloride with you, literally, right? You can try like you can plug in different concentrations, right, of each one, which you should always start out with a very, very large amount of the zinc, right? And sorry, the copper, a very large amount of the copper, and then a very small amount of the zinc, right? Until you get up to 13 volts, right? And then you can start your car. Like literally, that's how you can do that to figure out how to start your car. It's great stuff, isn't it? No, seriously, like if you had a copper electrode and a zinc electrode, and you had copper chloride and zinc chloride, and you just plugged in like a really big number for the copper, and then a very small number for the zinc, right? Try to make it as big as possible, like as much as you can do, and do it as much as you can until you get up to 13 volts. You can literally hook that up to your car and start your vehicle with it if your battery was dead. Like I'm no joke. Credit doesn't go to me because people have been doing it for a long time, right? Like people figured this out a long time ago. So, but yeah. So the only type of like actual calculation you'll have to do in this particular section right here is with this Nernst equation and figuring out that kind of stuff right there, right? Okay. And then that's probably like the hardest one, the hardest type on the exam. This kind of stuff is real easy. It's like just plug and play, like plug in the numbers and then get the answer, right? But this one here is a little bit more difficult because you have to figure out what the KEQ is, right? The Q is, and then also plug in calculations, concentrations. Okay, so that's the hardest thing you'll be doing on this exam as far as math goes for electrochemistry. So that takes us to this question here, which I don't even know if I should let you guys do it since no one's phone works. Huh? I thought there was three of you guys that didn't have phone working. I could have sworn I thought it was you, Mary, Naraya, and Oceana wasn't working. Yours is working? Oh, okay. Then it is just two. Sorry. Okay, so in this question, which of the following is true about redox and free energy, right? Spontaneous redox reactions produce a positive self potential, right? Or EMF. Gibbs free energy is a measure of spontaneity, so a positive EMF corresponds to a negative delta G, right? Or they're related by this equation here, which hint they are related by that equation, right? Or all these statements are true. I haven't counted them up yet. You talking about the house cup? Yeah, I haven't counted them up yet. You will find out on final exam day. That's why I'm not going to tell you, because if you know about it already, you might not have motivation to even come to the test. 20. We decided to combine them, right? Then we decided to combine two houses. No, I'm doing this in two. I'm doing this in two classes, right? And it's always been 20 points, and then people that don't get first place will get something lower than that. So since we combined both of the teams to like Slytherin, what was it? Slytherin. Yeah. So Slytherin, Ravenclaw, and then Hufflepuff and Gryffindor. It's just going to be 20 points for the team that wins, and then 10 points for the team that loses. Well, that's very optimistic of you. So, okay, what is the answer here? D. It is indeed D. Good job. Okay, so right here, this is something that's called a concentration cell, right? This is something that's called concentration cell, and this is the basis for how electric eels work, right here, right? If you have a solution, right? If you have a solution of nickel, some kind of nickel salt, like nickel chloride or something, that's why it's green probably, nickel chloride, okay? And you have a very small concentration of nickel chloride over here, and a very large concentration of nickel chloride over here, equilibrium is going to make it so that both concentrations are going to end up being the same. They want to make it the same, right? It's a lot like isotonic, hypotonic, and hypertonic solutions, right? Huh? Oh, salt bridge is literally just like Jello. It connects the solutions to each other. Yeah, because it's got salt in it. Like remember, salt is not just sodium chloride. In chemistry, salt can be any ionic compound, right? And so in an attempt to become the same concentration on both sides of this concentration cell, electrons will flow from the anode side over to the cathode side, right? And while it's doing that, you can actually get a voltage from it, right? You can actually get a voltage from it until it reaches this point where both concentrations are the same, right? So it's kind of a lot like equilibrium. Does that make sense? So say you didn't have any, if you say you didn't have any copper chloride or copper electrodes, but you did have two nickel electrodes and you had some nickel chloride, right? You could do the same thing again, right? And make a huge amount, a very, very little amount of nickel chloride on this side and a large amount of nickel chloride on that side, right? And do the Nernst equation and figure out figure out how much you needed to get a voltage of 12 volts, and then you can start your car. Or actually 13, you need 13 volts to start your car, right? Even though you have I don't know if you knew this, but 12-volt batteries in your car actually are not 12 volts. They're actually 13.9 volts. Right. Almost. That's how you can remember it. Because once your battery falls to about 12 volts, it won't start your car anymore. It's got to be way more than that for it to start your car, right? It's crazy stuff. Crazy stuff. It's kind of like when you buy power tools. I got a bunch of power tools for Christmas. I know I shouldn't know about that, but I got a bunch of power tools from DeWalt. And DeWalt has this thing called the 20 volt max power tools, right? Or batteries, XR batteries. They say it's 20 volts, but that's just the maximum it can be. The actual voltage is 18 volts, right? So oftentimes when you see voltages in media, in commercials, and in stuff that you buy, it's always a different number than it actually is. For batteries, 12-volt batteries are actually almost 14 volts. If you go below 12 volt, get even close to 12 volts, it's going to be very hard to start your car, right? And on the other side of it, it's the 20-volt batteries on DeWalt, right? So you can go both ways. It's crazy stuff, man. Learning new stuff all the time here in chemistry class, right? So notice that the Nernst equation implies that a cell can be created that has the same substance on both electrodes, and that's called the concentration cell, right? So that's this right here. This is the concentration cell. I'm going to ask you a question on the exam. Which type of cell has the same solution on both sides? What is it? The concentration cell, right? Because there's nickel on both sides here, okay? And then for such a cell, the cell potential would be zero, but Q would not be, right? Therefore, as long as the concentrations are different on either side, like almost nothing on one side and really high on the other side, the E will not be zero, right? The E will not be zero because you're always going to have that voltage flowing until the concentration is the same on both sides. Make sense? Right? Any questions about that? Okay. So let's talk about batteries then, right? The application of cells. Electrochemistry can be applied as follows as batteries, a portable self-contained electrochemical power source that consists of one or more voltaic cells. Batteries can be primary cells, which cannot recharge when they're dead, right? Or secondaries that can be recharged, right? They can also be used to prevent the corrosion or rust proofing, or they can be used in electrolysis, right? So here's some batteries. You have the lead acid battery. This is the battery that's in your car, right? And this is the one I'm talking about that is labeled as a 12-volt battery, but it's actually in actuality what? It's like 14, almost 14 volts, right? There's the alkaline battery, which is the one that you most know, double A's, triple A's, those kind of things. Then there's the nickel cadmium or nickel metal hydride batteries, right? Cadmium's toxic and heavy, so hydride batteries are replacing it. And then the lithium ion batteries, right? The lithium ion batteries are the ones that are in your power tools, they're in your phone, they're in your laptops, right? Those are all the types of batteries you should be familiar with. Okay? So here's a lead battery, okay? So and it even looks like a car battery, right? It looks like a car battery. So the electrolyte here, the solution here, right? So in the previous solutions, we had things like nickel chloride, we had, copper chloride, stuff like that. But in a lead battery, right, the cathode is lead, right? Uh, um, is lead based, right? And the liquid, the solution here, has sulfuric acid in it, right? That's the reason why when you have a car battery, you've got to dispose it properly. You can't just throw a car battery in the trash. You have to take it back to Walmart and they dispose of it, right? That's why they give you back $35 when you get replace your car battery, because they call it the core replacement fee, right? And that's because they're encouraging you to please bring back your dead car battery because it's dangerous and you don't want to just throw it in your trash, right? It's also for environmental reasons. Okay. In a alkaline battery, so this is like a shortened version of like I guess a double A or a D battery, right? The anode here is zinc plus some calcium, potassium hydroxide. The cathode here is manganese oxide plus graphite. And so, as you already know, right, electrons flow from the bottom to the top, right? Good stuff. Here we have a lithium ion battery, the same kind of battery that's in your phones, your laptops, your power tools, okay? The anode is on this side right here, and the cathode is on this side, and the thing that separates them here, the electrolyte, is the lithium, and that's why they call it lithium ion, right? That's why they call it lithium ion, okay? Current, again, flows from the anode over to the cathode, right? And if you didn't know this, the vast majority of the batteries that are in phones are all around 3.8 volts, right? So oftentimes people will try to buy other phone batteries from eBay or something that are claiming, man, these batteries are way stronger. They have 4 volts. You'll get more runtime on it, right? But no, the vast majority of it's all scam. The vast majority of them are 3.87 volts is actually what it is, right? Or 3.7 volts, somewhere around there. Okay, so don't fall for that marketing scam, right? 4 volts just means that, right? The same way 20 volts means 18 volts in power tools. Okay, so next question: which of the following is an example of a battery? We have the lead acid battery, the nickel cadmium battery, the nickel metal hydride battery, or all these batteries are actually batteries. Since you just got here, Aubrey, you're going to have to be in the second group of people to go do your test, your lab. Did you see the email I sent about having to split everybody up? Yeah. Everybody signed in on this one? So the answer for this one here, right? I don't even want to check to see how many people got it right. But the answer for this one here is that they're all types of batteries. Okay? So we also have this thing called the fuel cell, right? When a fuel is burned, the energy created can be converted into electrical energy. Usually this conversion is only about 40% efficient. That's probably why you don't use fuel cells everywhere, right? And then the direct conversion of chemical energy to electrical energy is expected to be more efficient on the basis for fuel cells. But fuel cells are absolutely not batteries. They're a source of energy that must be continuous. There's a source of energy must be continuously provided. So here's a hydrogen fuel cell, right? And so in a hydrogen fuel cell, right, hydrogen and water come from water, form water, sorry, mistype there, from water. The cells are twice as efficient as combustion, right? But the cells use hydrogen as a gas and then fuel as the hydrogen gas as the fuel, right? Because hydrogen is actually flammable, right? And then oxygen from the air, right? Oxygen from the air. So your next question is this: which of the following is not true about fuel cells? Fuel cells are batteries. In this cell, hydrogen and oxygen come from water. Sorry about that. The cells are twice as efficient as combustion, and then the cells use hydrogen as a fuel and then gas, oxygen from the air. I'm going to go ahead and tell you that the answer to this one here is what? A. Fuel cells are definitely not batteries. Okay. So what happens when corrosion occurs, right? Common name of corrosion is called rusting. It's also known as oxidation, right? So here's a water drop, and it's sitting on top of a piece of iron, right? And iron here, right, is actually getting oxidized. It's getting oxidized to form iron oxide, right? And so when that happens, you get rust. And the rust that you see is that red stuff right there, right? Literally, the rust that you see on things is iron oxide being formed from iron getting oxidized. It's crazy stuff, right? How do we prevent corrosion then? Well, you can prevent corrosion uh, by using zinc because zinc is actually more easily oxidized than iron. So oftentimes what they'll do is they do this thing called the sacrificial anode, and so the thing that gets oxidized first will get rusted, right? And then the thing that you don't want to get rusted, the iron, won't get rusted. So that's called a sacrificial anode. Kind of cool, right? So here's a picture of that, right? So if we have zinc there, okay, zinc here will go through the process instead of the iron will, right? And so the iron will not be oxidized, right? The iron is not oxidized, but the zinc will be oxidized. So oftentimes what happens is that you get iron at the bottom and you get a zinc coating, and then we have a zinc coating, you protect the iron from getting rusted, okay? That happens a lot, of course, in pipes underground, right? You don't have to answer this one. I just want to keep on going because I only have a couple slides left. I want to finish this. Okay. So there's also this thing called electrolysis, and that's why I actually have this up here, right here, this little beaker and this little 9-volt battery right here, right? Because I wanted to do a quick demonstration for you, right? And in electrolysis, what you can actually do is you can run a voltage, right? Run a current through, of course, we already know, molten sodium chloride, molten sodium chloride. Remember that regular salt by itself can't conduct a current, but when you melt it, it will conduct a current, right? And when you do that, you actually make some chlorine gas from the chloride side, and you make some sodium metal, right, from the sodium side, right? Same thing can happen over here with nickel and steel, okay? So the reason why I wanted to show you this, though, is here I have salt water, right? Here I have salt water, and I have two electrodes connected to a 9-volt battery, right? And when I stick the electrodes into the water, right? The salt water. Ouch, ouch, right? What you can see is, do you see bubbles being formed on the left side, the right side? You see the bubbles, right? You see the bubbles? You saw this in my office a second ago. You see the bubbles being formed right there? Yep. You see the bubbles being formed on the your right side, right? The right side electrode. Yeah. So I'll tell you what's happening here in just a second. You see the bubbles, right? See the bubbles? Yeah. So what's actually happening here, right, is that when we do this, this is actually doing an electrolysis where we're splitting the water molecules in half, right, and turning the sodium chloride in the water into sodium hydroxide, the base, right? So the gas that you see that's coming up over here on the cathode side, on your right side, that gas is hydrogen gas being produced. Hydrogen gas, right? Because remember that H2O, right, and sodium chloride, you only need one H and one O to make sodium hydroxide, right? So what happens to the other H? It becomes hydrogen gas, right? And that's what's being produced here in this electrolysis, right? And so interestingly enough, on the other side, right, the anode side, can anyone tell me what's being produced on the anode side? We already have the oxygen being a part of sodium hydroxide being made. We have one hydrogen being made, right, from the sodium hydroxide. The sodium is going to sodium hydroxide. What is left? No, we're talking about this. Chlorine, right? So literally what's being made on the right side, my right, but your left, right, is chlorine gas. Now someone tell me why you can't see the bubbles from the chlorine gas as much as you can see the bubbles from the hydrogen. There's a very chemical and very obvious reason why you cannot see the chlorine gas being made, right? But you can see the hydrogen gas being made. Think about the solution right here, right? What is this a solution of? Yes. What's got more there? What's the solvent and what's the solute? The solvent is the water. The solute is the what? The salt. What's in greater abundance? The water is, right? There's a crap ton more water in here than there is what? Salt. That's why you can only see what? Hydrogen gas being made instead of the chlorine gas on the other side. Does that make sense? Right? Your chemistry is supposed to make sense to you, right? The numbers that you read, the numbers that you get on batteries, everything you do in this class is supposed to make sense in your everyday lives, right? If you have a crap ton of water and just a little bit of salt in here, right? And you're making chlorine gas from it and you're making hydrogen gas from it, right? What's more which one is going to get more made of? The hydrogen gas, because it's mostly what? Water, right? It's mostly water. Now you sit there long enough, you can accumulate some chlorine gas and maybe make like a chlorine bomb and throw it in my office or something and kill me if you wanted to, right? After the tongue lashing I gave you earlier today. But anyway, so this is the last of it, the last of this lecture, the last lecture we're doing in this entire semester, right? It is very sad because I really want you to come away from this class seeing how, uh, seeing the world in a different way where you actually know what's happening in the world, right? So electrolysis is non-spontaneous reactions, right? Non-spontaneous reactions can occur in electrochemistry. How do you do a non-spontaneous reaction? This this is a non-spontaneous reaction, right? Turning sodium chloride into sodium hydroxide is a non-spontaneous reaction, right? But we can turn it into a spontaneous reaction by doing what? Adding in some energy, right? Putting in a battery, right? So that's why it says if an outside, right? If an outside, so it's not even spontaneous now. You're just driving the reaction, right? Using outside electricity source. Does that make sense? Right? And then if you use an electrical energy to create chemical reactions, that's called electrolysis, which makes sense because you're breaking the water in half, right? And that's the same thing as doing a lysis, right? And what are you using to do that? Electricity. That's why it's called what? Electrolysis, right? Or electrolysis, to be fast. Then these are all the things that you need to know, right? All the different terms you need to know, right? Which you can just look at that later. I'll give to you on the test, right? You have the Coulomb, which we talked about a second ago. It's in Faraday's constant. Here's Q. There's Q, the charge, the Q of the current. I don't think you really need to know that stuff. I won't ask you about that. You don't need to know about time, but you do need to know the number of electrons, and you do need to know the Faraday's constant. I will give you equations, but I will not give you constants, so you need to memorize those, okay? And there's like 3 constants to memorize. That's it, okay? And that actually ends today's lecture because I just told you all that just a second ago. You don't even have to read that part, right? And we're going to end with this question right here. Answer this last question and we're done for today. And then we can split you guys up for the lab. Well, we already split you guys up. Which of the following is not true about electrolysis? Non-spontaneous reactions can occur in electrochemistry if an outside electric source is used to drive the reaction. I feel like I just did that, right? And then use of electrical energy creates a chemical reaction called electrolysis. And then N equals the number of moles of electrons that can travel through a wire at any given time, okay? Just so you're not confused too, N can be the number of moles of electrons or just the number of electrons, okay? Like if you see, for example, on an equation, and it's like, a copper 2 becomes a copper, that's 2 electrons. You can use that too in the N, right? It doesn't have to be converted to number of moles. Okay? And so, to end this lecture and to end this class, the answer to this question is D, all the above. Okay? So, thank you very much, everybody, for attending class today and attending this class the entire semester. I hope you enjoyed it.